All right, something new. We are going to look at finding arc length in both rectangular and parametric form. So we're going back to our use of parametric functions. And here's what arc length is. The arc length is the length of the segment that you are traveling. So let's say on a graph that I go from like here up to here. Okay, well, the horizontal distance would be this. The vertical distance would be this. But what if I wanted to know the length of that curve? Not just horizontally or vertically, but how far have I traveled if I follow this windy path? That's what arc length is finding. It's finding the length of the curve, not simply just the horizontal distance or the vertical distance. Okay? Like, think of that like a piece of string. If we stretched it out so that it was straight, how long would it be now? So here are the arc length formulas that you do need to have memorized, okay? These integrals are almost always going to be calculator questions. They're just really unfriendly to evaluate by hand, and so these will certainly be ones that you can use a calculator for, as with most of everything in this particular unit. So if you have a curve defined rectangularly as f of x, then s, which is the symbol for arc length, s is going to be the integral from a to b, wherever your starting point and your ending point is, of 1 plus the derivative squared, all square rooted, dx. And this kind of comes from the distance formula. It's a little bit hard to see where that one comes from. You can see it a little bit better when it's defined parametrically. What we want when it is defined parametrically, when you have x is equal to f of t and y is equal to g of t, and we're looking at t values from a to b, it's going to be the square root of dx dt squared plus dy dt squared. And that's literally the Pythagorean theorem. If you have c squared equals x squared plus y squared, to solve for c, you take the square root. That's what we are figuring out, okay? And so here is how we would use this. So example 1 says find the arc length of the curve defined by x equals the arc sine of t and y is equal to the natural log of the square root of 1 minus t squared on the interval from 0 to 1/2. Now my first instinct when I see that natural log is to use my log properties to expand it out. And we may want to do that when we take our derivative. But again, we're going to use the calculator here. So let's talk about how we can set this up using the calculator a little bit nicely. This is where we want to be able to use our functions menu in the calculator. So I am going to set, we need to go ahead and find our derivatives first, and then we'll go ahead and set our calculator. So we need to find, to start, we need to figure out what dx dt. So the derivative of arc sine of t is going to be 1 over the square root of 1 minus t squared. I'm 90% confident on that. Then dy dt, it might be t squared minus 1, but I'm almost positive that it's 1 minus t squared. I don't have it in front of me. Dy dt is going to be equal to, now to take this derivative, I would go ahead and use my log properties here to expand. This is going to be 1/2 the natural log of 1 minus t squared. It just gets rid of that square root and makes our chain rule a little bit nicer. So this is going to be 1/2, that's just our constant multiplier, times the derivative of natural log is going to be 1 over 1 minus t squared, but then we have to multiply it by negative 2t because of the chain rule. So the 2's divide out, we're left with negative t over 1 minus t squared. Okay, now we want the interval from 0 to 1/2, so that's how we're going to set up our integral here. So here's what we've got. We know that the arc length, s, is going to be equal to the integral from 0 to 1/2 of the square root of 1 over the square root of 1 minus t squared plus negative t over 1 minus t squared. Oops. dt. I don't know where that little dot came from. That's not supposed to be there. There we go. Okay, now this is ugly. And this is even uglier to try to type in your calculator, especially if you're working one of the older models like mine, because I just refuse to spend money when I have one that works just fine, even though it's a pain in the butt. I would go ahead and define this function as y1 and define this function as y2. Then when you put this in your calculator, you can define a new function that is y1 squared plus y2 squared. Now, if you're like, I don't need to do that on my calculator, I think most of you have the new ones, fine, go for it. So I'd like for you to pause the video and try entering this in your calculator before we move on. Take a second to do that. I'm going to come back here with the answer in 3 seconds so that you can kind of calibrate and see if you're typing this in correctly. Now, sometimes these integrals can take a second for the calculator to run, so just let it think, but the answer that I get is approximately 0.549. That is what you should get. Now, once again, the way that I typed this in, and especially if you have one of the older ones like me, when you hit Math 9, you're going to get that function integrate message. And so I typed in the square root of y1 squared plus y2 squared. And then you have to tell it with respect to x from 0 to 1/2. I just use 0.5. And then when you put that in, that's what you should get. Now, even if you have one of the newer ones, I would still recommend that you use this y1 and y2. It's just fewer places to make a mistake when you're setting up your integral. Okay, so really this is just practice pushing buttons. You have to remember the formula first and foremost, and then you have to practice pushing the buttons. Okay, let's look at a couple more. Example 2. It says a circle of radius 1 rolls around the circumference of a larger circle of radius 4 as shown. So this is kind of weird. It would be like if you have a quarter and you take a penny and kind of rotate it so that it circles the outside of the quarter. So this is called an epicycloid, and it's traced by a point on the circumference of the smaller circle that is defined by this pair of parametric functions. We want to find the distance traveled by the point in one complete trip around the larger circle. Now, we always want to think smarter, not harder. We don't necessarily need to go all the way around the whole circle when we know that we're going from 0 to pi halves. That's a quarter of the circle. It's probably easiest to just find the smallest section that we can that is then going to repeat. So if we just go from theta equals 0 to theta equals pi halves, we're going to find essentially this petal right here, as we could call it, thinking about like a flower. Then once we get that, we can multiply it by 4. So we need to start by finding our derivatives. So this is what you should have for your derivatives, and this is what we can enter into y1 and y2 in our calculator. So the arc length that we want is going to be 4 times the integral from t equals 0 to t equals pi halves as we go around that circle of, once again, it's the square root of dx dt squared plus dy dt squared dt in this case. Go ahead and plug that in your calculator, pause the video, and guys, do it. Pause and practice with your calculator because this is the trickiest part of these. So pause the video while you type this in and come back for the answer in 3 seconds. You should get 10 for the integral and then multiply it by 4, so you get 40. So that is how far that sort of weird squiggly circumference ends up being. All right, here's one that's just a regular function. So we want to find the arc length of the graph of this equation y equals x cubed over 6 plus 1 over 2x on the interval from 1/2 to 2 as shown. So it's, again, we're finding the distance of that little piece on that weird looking curve there. It's not a parabola quite, but something kind of similar. So we need to start by finding the derivative. So y prime is going to be x squared over 2, and then this is going to be, 2x to the negative 1. So that derivative is going to be minus, because you multiply by the negative 1, 2x to the negative 2 times 2. So we get x squared over 2 minus 2 over 4x squared. And we can clean that up, but again, we're about to put it in our calculator, so it really doesn't matter. 1 over 2x squared is what that ends up with. So here's what our integral is going to be. The arc length is going to be the integral from 1/2 to 2 of the square root of 1 plus y prime squared dx. That's what we need to plug in. So we're going to put that in our calculator. Again, I'm going to ask you to pause, try it yourself, and come back for the answer in 3 seconds. The answer I get is 2.0625, so 2.063. All right. I would like for you to pause and see if you can do this final example on your own. Pause the video. I'll be back with the work and the answer in 3 seconds. All right, here is what you should get. Notice that when you take this derivative, you can use your trig identities to condense that down to tangent of x. If you put it in as sine over cosine, it won't be the end of the world, but it does make your life a little bit easier there. So that is how we can find arc length. Again, those are 2 formulas that you need to put on a flashcard and start getting memorized. Other than that, it's just making sure that you get it input to your calculator correctly. These are always going to be calculator active questions. So I'll see you back here next time.